I want to just review with everybody the ideal gas law. Most of you, or perhaps all of you, have seen the ideal gas law at some point in the past, probably in chemistry class. And the form you saw it in looked like this. PV equals N, I'm going to subscript with an M, R, T. This is temperature in Kelvin. This is the number of moles, which you'll remember from chemistry class. Pressure and volume, of course. Pressure in this case is in atmospheres, and the volume in this case is in liters. And if you do that, the constant becomes R is equal to 8.314. And if you look at the units, it must be atmospheres times liters per mole times kelvins. Okay, this is the version that the chemists like to use. It's a perfectly serviceable equation, and I'm sure you guys have done a lot of work with it, so I'm not even going to work in an example with you. If you want to check to see if you know how to use it correctly, try plugging in standard temperature and pressure, so 1 atmosphere and 25 degrees Celsius, and then 1 mole, and see what volume you'll get out. You should get 22.4 liters. As many of you also may recall. Now, I want to show you the version the physicists like to use, which is very similar, but has some important differences. We say PV, where in this case, if you guess, you probably will guess the pressure in this case should be in pascals, as in last semester, and the volume, of course, is in cubic meters. Okay? And then in this case, we go times N, no subscript, KBT. And now here, T means the same thing as before, temperature in kelvins. N is the number of particles in the gas. Particles could be either molecules, it could be atoms, or it could be a mix of both, depending. For instance, Earth's atmosphere has some free atoms, as well as a whole lot of molecules in it. It's just the total number. In KB, your book calls it just K. I call it KB, partly because I really think that Boltzmann deserves a little credit for this, and partly because we use K for so many things, it really does need a subscript, to be honest. KB is equal to 1.38 times 10 to the minus 23rd power. In this case, it's in pascals times meters cubed per Kelvin, and particle maybe. This one is one of those units like radians you can kind of drop sometimes. KB, it turns out, is one of the most important constants in physics. It, we will see, relates not just the ideal gas law, and by the way, it is related to Avogadro's, or to R via Avogadro's constant. You can go ahead and verify that for yourself if you want. But it also relates the amount of energy in a gas, or in a molecule, the gas, at least, to the temperature directly. And we will see that in just a little bit, in another video. But this is a really important relationship, and it pops up all over the place in thermodynamics and in statistical mechanics. So it is one of the most important constants in all of physics. Okay? One final way of writing the ideal gas law I'm going to share with you that I don't think the book covers, but I really want to, is I'm going to divide both sides by the volume. And then I'm going to get P is equal to NKBT, where N is the number of particles per volume. This is a kind of a density. Volume. There we go. Kind of a density here. It's not a mass density, not a mass per volume. It's a number of particles per volume. They're related, and I'll let you figure out how. But this is actually even in simpler form, and it turns out this form, and the form that chemists like to use, is useful if you have a fixed volume. If you've got a reaction vessel, a beaker, a flask, whatever, and you're doing something inside of it, which sometimes you are. Chemistry, usually you are. Physics, sometimes. But a lot of times we're kind of working where there's no real obviously fixed volume. Like if we're talking about atmospheric stuff, you can't really talk about the whole atmosphere because there's too much variation in things like temperature and pressure through it. But you can talk about locally, like a little patch. Imagine sealing off a bit of air, in Olympia, for instance, and then say, okay, what's going on here? But it's not really sealed off, in which case we could talk about how many particles are in each cubic meter. That's our N, and then this relationship still holds. So it's a different version, but I think it's a helpful version. All right, next video will be about energy and velocity in ideal gases.